Right. So we have this stack of sources in front of us that I think is going to completely redefine how you look at some of the most powerful hardware out there.
I think so too. Yeah.
Usually when we talk about NVIDIA or just the GPU in general, what are the top three things that jump into most people's minds?
Oh, gaming for sure. Then crypto mining, although maybe that's a bit less of a hot topic
A
now.
little less, yeah.
And of course, the absolute explosion in AI, large language models, chat GPT, all of that.
Right, those are the usual suspects. And it makes total sense. That's what drives the consumer market.
Absolutely.
But if we actually peel back the layers and we look at what a GPU is really doing at a fundamental level,
Yeah.
especially based on this material here about electromagnetic simulation, what's the one phrase we should really be thinking of?
It's all about solving Maxwell's equations.
And that's the hook right there. It's a complete change in perspective.
It is.
Most of us see a GPU as, a graphics card or maybe an AI accelerator. But these sources, they make this incredibly compelling case that at its core, the GPU is an engine built to solve the universe's basic physics problems.
Exactly. And that's our mission for this deep dive. We really need to get into the scale of the problem. We want to explain why designing modern tech, I'm talking about 6G antennas, new stealth materials, even the circuits inside a chip, why it's just computationally impossible for a normal computer.
The computational cost, as they call it.
The cost of simulating reality is just too high for the old way of doing things.
And we're going to show you how the very same hardware that's rendering your video games is pretty much the only thing preventing a massive innovation bottleneck. So let's start with the scale of it all.
Let's do it. So we're trying to simulate something like a radio wave. Could be Wi-Fi, it could be a new 6G frequency.
Okay.
As an engineer, you can't just tell a computer, okay, I send a wave from here, tell me where it ends up.
Right, but why not? I mean, if I know the power and the frequency at the start, shouldn't a computer be able to figure out the end result pretty fast?
It could, yeah, if the wave was just traveling through empty space, a vacuum.
But it's not.
It never is. For the kind of accuracy you need in real engineering, like designing a phone antenna that works perfectly, you have to model how that wave interacts with everything, every single reflection off a wall, every bit of absorption, every time it bends.
So you have to model the physical space itself.
You do.
And that brings us to this idea in the source material, the 3D array.
The 3D array, or the computational grid. It's basically how the computer sees the world. You have to slice up the entire space you're simulating, say, this room, into tiny, tiny invisible cubes.
The Minecraft world analogy they use.
It's a great analogy, but there's a really critical catch.
And that would be the size of the block.
Exactly. The size of the block determines how accurate your simulation is, and the physics tells you how small they have to be.
So to model a wave properly, you need to have multiple blocks per wavelength.
You got it. So for something like AM radio, the waves are huge, meters long. Your blocks can be pretty big.
But when you get to the cutting edge stuff, like 6G,
The wavelength just shrinks dramatically.
it's tiny.
So tiny that those little computational cubes, they have to be microscopic.
Yeah.
Way, way smaller than the things you're actually trying to design. And that is where the scale it explodes.
Let's put a number on that. So if we take, say, a normal size room, maybe 5 meters across, and we want to simulate a 6G frequency in it, how many of those little blocks are we talking about?
You very quickly get into some wild numbers. To get the accuracy you need, you're easily looking at over 1 billion blocks.
1 billion.
1 billion unique cells, yeah.
Okay.
1 billion data points just to describe the room before anything has even happened.
1 billion cubes is. That's already hard to get your head around, but that's just space. The next problem is time, and that's where it gets really crippling.
It is, because it's multiplicative. It's a snowball effect. We aren't modeling a static thing. We're modeling energy moving through that space.
And that energy moves at the speed of light.
Right. So to capture that, we have to chop up time into equally tiny slices.
Yeah.
We're talking nanoseconds.
So for every single nanosecond that the simulation moves forward, the computer has to recalculate everything.
It has to recalculate the electric field and the magnetic field, the two parts of Maxwell's equations, for every single one of those billion blocks.
Wow.
So if you want to simulate just 1 second of real time, which seems like nothing to us, the number of calculations just becomes, well, overwhelming.
So you're multiplying 1 billion points in space by billions of moments in time. That's how we get to that number in the source material. Quintillions of operations for just a few microseconds of data.
And that is the problem. That's the computational cost.
Yeah.
The math in each little block isn't hard. It's just Addition, subtraction,
Yeah.
simple stuff. It's the sheer volume that breaks everything.
Which leads us right to the bottleneck.
Yeah.
The CPU, the central processing unit.
Yeah.
We know CPUs are incredibly fast. They run our whole world. So if the math is simple, why can't we just throw a bunch of powerful CPUs at this?
It's because of what a CPU is designed to do. It's optimized for sequential, complex tasks. I love the analogy they use.
Yeah.
The CPU is like a genius math professor.
Okay.
It's unbelievably smart. It can handle an operating system, run really complex software, solve incredibly hard problems with precision.
It's built for deep single-file thinking.
Exactly. But it works sequentially. One thing, then the next, then the next. It has all this machinery for complex instructions for predicting what comes next, features that make it a genius.
But when you give it a billion simple, independent problems, calculate this block, then this block, then this block, that genius is basically wasted.
Completely wasted. And worse, it spends most of its time on the overhead of managing those simple tasks. It's like asking that one genius professor to grade a billion simple true or false questions in a second.
It just chokes.
It chokes. The system grinds to a halt. You end up waiting days, sometimes weeks, for one simulation to finish.
So the problem isn't a lack of raw power, it's the wrong kind of power.
It's the wrong architecture for a problem that physics demands be solved all at once.
Okay, so we've got the problem. Huge computational cost, and a CPU that's built for the wrong kind of work. So now we pivot to the solution, the GPU.
This is where parallel processing comes in.
Let's use that counter analogy from the source material. If the CPU is the single genius professor, the GPU is an army of 10,000 elementary school students.
It's a perfect contrast. A GPU doesn't have a few massive, brilliant cores. It has thousands of tiny, simple cores. These students, they aren't geniuses. They can't run Windows.
Right.
But they are fantastic at one thing, doing simple, repetitive math all at the same time.
And why is that army of simple processors so much better for this particular problem, for Maxwell's equations?
Because the physics problem itself is naturally parallel. What happens in, say, block number 5,000 is almost completely independent of what's happening over in block number 6,000 at that exact same instant.
They don't need to check in with each other. There's no central coordinator.
None at all. So you can give the exact same simple instruction, add this, move that, to all 10,000 students at the same time. The simplicity of the GPU cores becomes this massive advantage. You have 10,000 little engines all working on 10,000 blocks at the exact same moment.
And this is all harnessed through programming platforms like COA, right, NVIDIA's system. What is COEA's role here, just briefly?
CAD is the key. It's the language that lets engineers take a problem that would normally run on one CPU and map it or spread it out across those thousands of GPU cores.
So it changes how you even think about writing the code.
It completely changes it. You stop thinking, do step one, then step two. You start thinking, take this giant problem, give a small piece to every single one of my 10,000 workers, and then just collect the results. It lets the software mirror the physics.
Okay, let's get to the results, because this is where it gets really mind-blowing. What happens when you take that old simulation written in C for a CPU and rewrite it for a GPU using CUDA?
The jump in speed is just. It's transformative. It's not a small improvement. The examples in the research show that you can get speed-ups of up to 500 times faster.
500 times? That's not an upgrade. That's a revolution in how you work.
It totally is. It takes the problem from being, something you can do in a university lab if you're patient, to something you can use for actual practical design work.
The concrete example they gave. A simulation that used to take a whole week.
A full week, tying up a super expensive computer, making a whole research team wait.
And now,
that same job finishes in 20 minutes.
20 minutes.
Think about what that means. You're not waiting a week to find out if your new antenna design is a failure. You can test hundreds of different versions, move things around, try new materials, all in a single afternoon.
You can fail fast.
You can fail fast, and that speed of iteration is what drives all modern innovation.
That's the bridge. That's how we get from 5G to 6G. That's how we pack more and more onto a tiny chip. You can solve problems in minutes that would take a generation to solve before.
Yeah, without a doubt. Without this kind of acceleration, the complexity of modern electronics, especially putting antennas and high-speed connections on tiny chips, that whole field of engineering would have just ground to a halt years ago.
Which brings us to this just fascinating irony in all of this self-fulfilling loop. The hardware is literally designing its own future.
Yes, it's a perfect circle. We are using today's NVIDIA GPUs, which are themselves amazing feats of engineering, to solve the physics of light and electricity.
To solve Maxwell's equation.
Exactly.
Yeah.
And the whole point of doing that is to design the next generation of hardware, the next GPUs.
So the tool is literally creating its own successor. What specific things are being designed this way?
Well, a huge one is designing the next lithography machines, the machines that use light to etch patterns onto silicon
They make the chips.
to make the chips. If you're trying to draw lines that are 5 nanometers wide using light, you have to know precisely how that light is going to behave.
So you have to solve the physics of light millions of times in a simulation before you even build the machine.
Absolutely. And you're also designing the components on the chips themselves, the tiny little antennas and pathways needed for super fast communication inside the processor. You need that predictive power.
So the 6G technology we keep hearing about, all the promises of insane speeds and low latency, that would literally be impossible without the GPUs that were designed to solve the problems of 5G.
It's a continuous closed loop. The speed of our GPUs has basically become the speed limit for how fast our technology can advance. Faster GPUs mean better design tools, which means better physical chips, which then become the next generation of faster GPUs.
This has totally reframed things for me. The same piece of hardware that's all about entertainment, about getting high frame rates in a video game,
Yeah.
is the same engine that's designing our entire global communication infrastructure and the future of every electronic device.
It's this beautiful bridge between pure science and real-world engineering. You have this massive army of simple processors just crunching the laws of the universe so we can all have faster Wi-Fi.
So the core takeaway for you listening to this is this. Don't just think of a GPU as a toy for gaming or a niche tool for AI. It's become a fundamental necessity for engineering the physical world around us.
It's how we overcome the computational cost of reality. The ability to simulate the world efficiently is what sets the limits on what's possible.
It's the architecture, not the physics, that's the bottleneck.
Exactly.
Okay, so here's a final thought to leave you with, something that builds on all this. We've talked about how the GPU lets us solve these known laws of the universe, like Maxwell's equations, practically in real time.
Right.
So think about the implications of that speed. If time is no longer the main barrier to modeling physics, what can we design now? What kind of revolutionary new materials or previously impossible engineering feats can we now even attempt that were just too computationally expensive to even think about 5 years ago?
Once you break down that computational wall, the horizon of what's possible
Huh.
it starts expanding exponentially.
Thank you for joining us on this deep dive into the physics engine that's been hiding in plain sight.